Okay, let's get started. Okay, so let's review what we covered in our last lecture. So in our last lecture, we finished talking about the chapter 7, and I think the homework is due today. So hopefully you can do all of them now. And so for the last part of the chapter 7, so we cover the feedback capacity. Right. So the key point here, or something to be aware of is that, so normally the feedback capacity should be larger than the capacity without the feedback, right? But we show that, so actually the capacity is not bigger than the capacity without feedback, right? Actually, they're the same. Okay, and in order to show this, so we need to show again the achievability and the converse, right? And for the achievability, we don't need to show anything, right? Because if without the feedback, we can still achieve the same thing, right? So we just, achievability just, we just use the random coding argument without feedback as what we did before, right? But the trick part is the converse. Okay, how can we show the converse? So here, so we show again that we should use the normal 5-step converse approach. Right? Of course, we need to tune it a little bit because the data processing inequality cannot be used, right? So we need to be aware of that. Okay, and so yeah, that's for the feedback capacity. Although we say, okay, if the feedback capacity is the same as the capacity without the feedback, but it doesn't mean that the feedback is not useful, right? First of all, so what we care about here now is the point-to-point DMC channel. Right? If it's not DMC, it's with memory, then feedback may help, right? We may get a higher capacity, right? And if it's not point-to-point, it's a multi-user channel, then the feedback can still be helpful. We may get a much higher capacity in that case, okay? So, and in addition, so if we take the complexity into the consideration, and then the feedback may significantly reduce the complexity of a coding scheme, right? For example, for the channel without feedback, we need a very large n, right? Very large code length, right? For example, okay, and then we need to design a very complicated code book, and we need to decode that, right? That can be very complex, right? And we show that with ARQ, right? And with just simple feedback to tell us whether there's an error or not, and if we consider that in a BEC channel, we can show that it's more or less achieve the capacity. Okay, so so the scheme is very, very simple. Okay, so in terms of the complexity, feedback can be very helpful. Okay, just remember that. So we do not claim that feedback is not useful, even for the point-to-point DMC channel. Okay, it's just for the metric of channel capacity, where we let n goes to infinity and error goes to 0. In this case, it happens that the feedback channel capacity and the capacity without feedback are the same. Okay, and then we introduce you the source channel separation theorem or the joint source channel coding. So similar story here, right? So those are the definitions when you define encoding function, decoding function, and average error probability. Right? The reason we do not consider maximum error probability here is that we don't need to consider that. Right? Once we show the average error probability goes to 0, then there's a way to show the maximum error probability will be 0. Okay, and here is the definition of a transmissible, and the conclusion here is that, so basically again, so the separated source channel coding does not lose anything in terms of the capacity, okay, or the coding rate, okay, because we can show this theorem, right? So this easily can be achieved by the source channel separated coding scheme, right? So basically, so it's like what we do in practice, right? If we do the compression first, right, and then first we do a source coding for compression, and secondly, we do a channel coding, and then we do the transmission. So yeah, it can achieve exactly this. Okay, so again, it doesn't mean that the joint source channel coding is not helpful, right? So it may reduce the encoding and decoding complexity, but it will increase the system design complexity possibly, right? Because when we design any coding scheme, we need to consider the channel, right? So, but if we do the separate source channel coding theorem, so for the source coding part, we don't need to consider the channel, right? We can just apply a unified source coding theorem, source coding scheme, like the Lampo-Zip coding, right? Like arithmetic coding, Shannon code, Huffman code, whatever you want, right? And then once you achieve the more or less the entropy and then or entropy rate, and then you can apply any good channel coding scheme, right? So that is what we use today. Okay, so this theorem guarantees you that if you do that, you are more or less optimal, right? But it doesn't mean that you cannot get any gain if you do the joint source channel coding. Okay. All right, and for the proof, and the achievability is exact the separate source channel coding, proof, right? So it's pretty straightforward, and right. So here, what we do is that we use the typicality encoding for the source coding and the random coding for the channel coding, okay? And then you can show that. And for the converse, again, so it's a 5-step proof, okay? So the procedure is exactly the same as before, but there's a tiny difference there. Okay, the tiny difference is basic step 1, right? Step 1, in the original channel coding theorem, we use NR equals to the entropy. Right here, we can now do that. Okay, so here, what we use is that, if you remember, right, we use the entropy of V power K is less than K times the entropy, or vice versa. Yeah, vice versa. Yeah. What I said is reversed. Okay. All right, so yeah, we use the the decreasing property of the entropy rate, right, basically. Okay, somehow you have to do this 5-step, right? But for each step, you need to it may be different. All right, so now let's see what we're going to cover today. So today we're going to start talking about our chapter 8. Number 32. Today we'll start talking about chapter 8. Okay, hopefully we can finish the chapter fast. So basically, this chapter is it's like chapter 2, but we focus on continuous random variable instead of discrete random variable. Okay, so basically the idea is that we want to apply everything we have studied so far for the continuous random variable, right? Because in practice, there exists continuous random variable, right? For example, like the noise, right? So the value are continuous, right? All right. So that's basically the idea, and we're gonna see how we're gonna extend from the discrete case to the continuous case, okay? And it's not very straightforward, okay? For some part, it is straightforward, but for some part, it's not. Okay. First, we're going to introduce you the differential entropy. Okay, so yeah, the counterpart of that is entropy for the discrete random variable, and then we're going to introduce you the relative entropy or the KL divergence. Okay, and then so relative entropy of continuous random variable. Okay, and then we're going to introduce you the joint and the conditional differential entropy. The joint and the conditional differential entropy. And number 4, let's see whether we have time to cover that or not. So we're going to introduce you the AEP for continuous random variable. Okay, so the idea still holds, but the presentation is a bit different. Okay, and lastly, we're going to talk about properties. Okay, again, the property is not so different. So the biggest difference here is the definition of entropy. Okay. Okay, so far what we have known is that we know for the discrete random variable, so the entropy, yeah, for the discrete random variable, So the entropy equals to this, right? X in X, Px log 1 over Px, right? So this is the definition of the entropy, right? Since we know that already, right, and we understand that pretty well, so now we want to extend it to the continuous time case, right? Let's see how can we do that, okay? So now, suppose the random variable x takes continuous values. So now our set of x is basically the real set. Okay, so it can be positive, it can be negative, right? It's a real set. And now the distribution of x is a PDF, probability density function, instead of a PMF now. Okay, so basically the PDF normally look like this. Okay, let's say, for example, so this is our PDF. Okay. So based on what we have learned for the discrete random variable, so can you think a way to define the entropy for the continuous random variable? Right, so what's the entropy? Yeah, how can you do that? Yes?
Could we swap the summation for an integral?
That's a good idea. Yeah. So we can now just swap it, right? So we need to somehow show it. But I think the idea is definitely valid, right? So basically, in order to show that, so what we do is to use calculus, right? So basically, it's similar to how can we derive the integral, right? How can we derive the integral? It's from kind of summation, right? What we do is that we partition this function in this way. So that's how we do the Riemann integral, right? So basically, yeah, let's do that. Okay. Okay. So we can do that. Very good. Okay. Once we do that, so basically, what we can kind of approximate here is as follows. So let's assume the integral here is, the interval here is I sub I, right? Yeah, let's label the bin somehow, right? Like for example, maybe you consider a simple case where we have a finite range here, right? And then we say, okay, so the function is defined from A to B, for example, right? And then we can label all the bins, right? So here the bin is I equals to 1, here's 2 and 3 and so on, right? And here is the ith bin, right? And we denote the interval as that. And we assume that all the intervals are the same, equal to delta, okay? And we can compute that, right? Let's assume that in total, let's say we have n bins. So basically, the length of delta is nothing but b minus a over n, right? So this basically is the size of the bin, okay? And so let's say we have many of those, right? Like what we do for the integral, right? So for the integral, what do we do is that, if the bin size, is very, very small, right? Then we can somehow approximate this area by what? By this value multiply the width, right? So now let's assume the value is basically fx or fxi, right? And then times delta. Yeah, let's use xi here. Yeah, xi is just the value here, okay? Because it's very small, then the xi, the difference of xi is very small, right? So this is approximation of what? The area of the bin, okay? And basically, and then this is how we do the integral, okay? And yeah, let's do the same thing here, okay? So basically, let's say when xi is, there exists xi in this interval, and we can definitely find such xi times delta equals to this guy, right? Why is that? Why is true? Exactly. So hopefully remember that from from your calculus, you learn that mean value theorem, right? So we can always find AXI such that we can do this. Very good. Okay, but now we are working on a PDF, right? Not just general function. Okay, so when we work on PDF, so basically, we can use a random variable to represent this guy. Okay, so this basically means that we use a random variable. Let's say we let x delta. So when that equals to I, basically means if x is in I sub I. Okay. Yeah, so basically, this represents the value of a random variable. Okay, so before the random variable can take a value, anywhere here, right? We assume that, when the bin is very small, and then we just say, okay, so this also represents a sort of equivalent discrete random variable, and the value of this random variable is I. Does that make sense? Okay, so now we have a discrete random variable. So now we can compute the probability of it, right? So the probability of x delta equals to I. So that will just equals to the integral over I and fx dx, by the mean value theorem. So that equals to this. Okay, which is the area basically, right? So we just restate what we just said. Okay, so now we have a random variable of x delta, and then we can compute the entropy of it. Okay, and then we let delta becomes very small. Then we say, okay, this probably can be represented by the entropy for the continuous variable. Does that make sense? Yeah, let's try this idea, see whether it makes sense or not, right? It's a very natural idea, right? Okay, so now let's just compute the entropy. Okay, so we have entropy of this equals to the summation, and we have the probability that x delta equals to I log probability that x delta equals to I, okay? And then we plug everything in. So basically, so this probability equals to this guy, right? So we have fx I delta log fxi times delta. Okay, and then we need to do some manipulation here, right? So one thing we can do here is we're going to separate these two, right? Because it's log. So basically, let's do this: fxi times delta, times delta log fxi, and then minus delta fxi log delta. Okay, very good. So any questions so far? Okay, so now what we can do is that we're going to move this delta to here. Okay, just move the delta from here to here, right? Just reorganize it. And then, so basically what we can do is that, okay, for this part, okay, when delta becomes very, very small, right? When delta becomes very, very small, so this can be approximated by what? By the integral, right? Then it becomes an integral over from a to b, fx log fx dx, right? So when, we may say this, right? Not approximately equal. So it will converge to this when delta becomes very small, right? So that's basically the integral, right? That makes sense? Okay, so now let's see what the later part. So for this part, what does that equal to? Right, log delta is a constant, right? It doesn't matter. But for this, what does that equal to? Yeah, it's another integral, but what, can you give me a value of it? What?
1, right?
Yes, that's 1, right? Because So this is the probability of xi, and then we sum over all of them, right? Then it's xi. Okay, very good. So now let's see what we got. Okay, so for the first term, it is this, fx log fx dx, right? And this is almost like the entropy formula for the discrete random variable, right? If you compare this and that, the only thing we did is to replace the PMF by the PDF and the summation by the integral, so which kind of makes sense, right? But the problem is the second term. So this is not enough. So we need to minus this guy. Right, so those together equals to the entropy of a discrete random variable. Okay, but when delta becomes very small, then this will equal to what? What? No. Yeah, it's a log, right? So when this becomes very small, delta becomes very small, the log becomes what? Negative infinity, right? Therefore, because this term, we get this term by using the fact that delta goes to 0, right? But here we cannot let delta goes to 0. Yeah, otherwise this term will become infinity. Together will be infinity, so it's meaningless. Then what do we do? Right, so this idea doesn't work, right? Seems. Yeah, so basically what we do is very brute force. So we just ignore that. Okay, we don't like it, right? So then why do we need to consider it? It's a definition. We can define whatever we want, right? So we brute forcefully define the differential entropy Hx as this guy. So now we consider a more general version. So AB can be infinity, right? That's it. Okay, but now we cannot call this entropy, right? Because this is not entropy, right? Because this is entropy, and this is not entropy. We ignore this term, okay? And the meaning of it is different, right? We know a clear meaning of entropy, right? But for this guy, so we ignore that. We cannot call that entropy anymore, so we call that differential entropy, okay? So that's a definition for differential entropy. The differential entropy of a continuous random variable x with PDF fx is defined as this. Okay, very good. So that's basically the differential entropy. Any questions so far? Yes.
Do we apply the same four axioms that we use to define entropy to this, or do they not apply?
Not apply. Very good. So that's our first remark, right? So because of we ignore the log delta term, right? Then basically the differential entropy does not have the same meaning as entropy, right? So basically there's no meaning of it, right? Because technically it should be infinity, right? So this basically tells you that in practice, when you cannot compute the entropy of a continuous random variable, right? If you want to compute it, it's infinity, right? It's meaningless. So you cannot compute the entropy of a continuous random variable.
Conceptually, though, doesn't that kind of make sense that the entropy would be infinite because it's continuous?
Oh yeah, yeah, definitely. Yeah, so basically it'll be infinity for all the distributions. So yeah, what's the point, right? Yeah, that's right. Yeah, so basically, this still holds, right? So we have a clear meaning of that, right? Just this guy will equal to 0, or equal to infinity for all distribution, right? So yeah, that's totally correct. And then we just take the first term, right? So the first term does not have any meaning. Okay, very good. So but it's not the end of the world, right? You'll see, so we can still somehow do it. So differential entropy is not a measurement of uncertainty. Okay, however, if you really want to do it, there's still a way to do it. Okay, however, if we really want to do it, then we can quantize the random variable, convert it to a discrete one, right? So in practice, usually what we do is that we let delta equals to 1 over 2 power n, for example, right? Have this quantization. So basically, exactly like what we do here, right? To have a discrete random variable. So that's a good approximation for the PDF, right? Technically, they are different, but in practice, we can, or in computer, so we can now really do a continuous random, PDF, right? So we can do discrete instead. So basically, if delta equal to that, we can compute the entropy, will equals to small h of n. Yeah, by the way, so for this differential entropy, we use small h, now using big H, okay? Then small h plus n would be our entropy, right? So that is the entropy, or also the number of bits on the average. Required to describe x to n bit accuracy. Okay, so very good. Okay, so yeah, this is the meaning of the differential entropy, right? So basically, it does not have very concrete meanings. Okay, let's see some example. Let's say some computation of differential entropy. So here, normally we only use two important distribution. Number one is uniform distribution, like what we do in the discrete case, and the other one is Gaussian distribution. Okay, so let's first consider the uniform distribution. Okay, we let x follows a PDF, and then so that's equal to 1 over a when x is in 0 to a and 0 otherwise. Okay, so now let's compute the differential entropy. So this is how we do it, right? dx. Okay, so because it's a uniform distribution, then we just have minus a multiplied 1 over a log 1 over a. Right, so that equals to log a. Okay, so that's pretty easy, right? Just for uniform distribution. So then the differential entropy of x is log a. Okay, note here, so the only thing we require a here is that a is bigger than 0, because the range is from 0 to a, right? So a can be less than 1, can be bigger than 1, right? So let's say, what if a is less than 1? So what will happen? Right, if a is less than 1, then hx equals to log a. It means that this is less than 0, right? So this is one big difference between differential entropy and entropy, right? So differential entropy can be less than 0, right? But entropy cannot. Okay. Differential entropy can be negative. Okay, so here is a pretty big difference. And so this is a uniform distribution. Next, we're going to compute the differential entropy for Gaussian distribution. Okay, Gaussian distribution. So all of you know what a Gaussian distribution is, right? So Gaussian distribution looks like this. The PDF is 1 over, so now consider just one random variable. Okay, square root of 2 pi sigma square e minus x squared over 2 sigma squared. So we assume the mean value is 0 and the variance is sigma squared. Okay, it's a mean 0 and variance sigma square Gaussian distribution. Okay, so now let's compute the differential entropy, Hx. Okay, so that equals to Fx log, let's plug that in. So later we're going to, we'll just fix the first Fx here to simplify the notation a little bit, and then we'll just see this. Okay, so we're going to do some manipulation of the second part, of the later part. So basically here, so we're going to break it. So the first term is minus half log 2 pi sigma square, right? And then we have a second term here. Also, we have a negative term, x squared over 2 sigma square log e dx, right? So here we do not expect any based on the log here, okay? So that's basically what we got. Okay, and then, so we can keep manipulating. So for the first term, we have fx, and we have half log 2 pi sigma square. So we have a minus here, and we have minus in front, right? Then we do not have this minus here. Okay, and for the second term, similarly, we have a minus here, and we have a minus here again. So we don't have a minus, we have a plus. That would take the constant in front, right? And then, so we can do this integral. It's x squared times fx dx. Okay, if we take that out, it's an integral of x over all the x. So that is what? 1. Okay, so that's a mistake. So then the first term will becomes this, right? Okay, so now it makes sense. So then we have what? Half log 2 pi sigma square and plus. So we have a sigma here and we have sigma here, so that sigma canceled. So we have this, okay? And then we can combine those two. So then we have half log 2 pi e sigma square. Okay, and that's the result, right? Okay, so this is the differential entropy of a Gaussian random variable. Okay, so that's very important. Yes?
How do you get sigma squared from the second integral?
Oh, that's the variance. So this equals to expectation of x squared. Right, so that's definition, right? X squared multiply fx to the integral. So this is the definition of the expectation of x squared. Okay. Right. Okay, very good. Yeah, so this is basically the differential entropy. Any questions? Okay, no question. Let's continue. So far, I think, so our result is not very optimistic, right? Because we do have a definition of differential entropy, but we don't have a strong meaning of it, right? So it can be negative, right? So we cannot use that to measure the uncertainty of a random variable x, right? So that's not very good. However, now let's check for other information quantity, right? Like relative entropy, mutual information, and so on. Right? Let's see how we can define those. Okay. Again, so in order to define those, we have to go back from the discrete random variable and try to repeat the same thing and see whether it makes sense or not. Okay. So second is relative entropy. Okay, for relative entropy, so we let fx and the gx be 2 PDFs. Again, so for simplicity, we assume they just distribute from A to B, so that can make our life easier. So similar as before, so basically what we're going to do is as follows. So we're going to partition the interval AB into capital N's intervals, okay? So say here it's I equals to 1, here's 2, 3, and so on. And the last one, the last one here is N. Okay, so this is basically what we do here. And again, so for any interval, so we call that I. Okay, and the length of I is delta equals to B minus A over N, right? So that's normally what we do. And then again, so based on that, we can define our discrete random variable, right? So our discrete random variable is as follows. We assume Pi equals to the probability that X delta, we use XF delta and the XG delta here. XF delta equals to the interval I, right? And then that equals to the integral of this guy equals to xi times delta. And we assume qi equals to prxg delta in I. So that equals to this and gxi delta. Okay, so that's basically what we do here. Yeah, so in order to distinguish, we'll denote that as xi prime. Yeah, because they may not be the same, right? I mean, this xi and xi prime may not be the same, right? It's from the mean value theorem. Okay, so now we have two discrete random variable and two discrete PMF now, right? So now let's compute what is the differential entropy dpx and the qx, right? When delta is very, very small, then so this basically equals to this guy, log pi over qi. Right, so this is the definition of the relative entropy for the discrete case, right? And then we plug everything in, delta times fxi log delta fxi delta gxi prime. Okay, very good. So now let's see what happens. Okay, so this delta and this delta got canceled. Okay, and then we can move this delta to here. Okay, so next step is the similar as before. So we're going to let delta go to infinity. It goes to 0. Okay, and then this term will become integral from a to b fx log fx over dx, and delta becomes dx. Right? Yeah, what did you find? It worked out, right? So there's nothing weird going on, right? So if we compare this formula with the with the relative entropy formula for the discrete case, they are exactly the same, right? So for discrete cases, so here's PMF, and now here's PDF. So we just replace the PMF by the PDF, and then it works. Right? There's no term we need to ignore, right? So everything works fine. So this basically means that the differential entropy can have the exact same meaning as before. Yes?
Can we ensure that the relative differential entropy would not?
No, it's not. It's not relative differential entropy, just relative entropy. Yeah, the reason we do not say it's differential entropy is that it has the same meaning as before. We don't need to have a different definition for that.
Okay.
Yeah.
So it will stay being like non-negative, right?
Yes. Yeah, because you can see, yeah, so everything here worked out. So all the property for the relative entropy before will hold here. even the meaning hold here. Okay, so now we have a clear meaning for differential entropy, for relative entropy. Right? We don't have a clear meaning for differential entropy, but we have a clear meaning for relative entropy. Right? Kind of weird, but not really. That clear? Okay. Yeah, let's write this definition down. Yeah, but it will be the same as before. So the relative entropy yeah, it's a good point, right? We don't call that relative differential entropy, right? Just relative entropy or the KL divergence. Between two PDFs, fx and gx, is defined as the differential entropy between f and g equals to d fx gx equals to this. Okay, the remark here is that the relative entropy of continuous random variable have the same meaning as in the discrete case. Okay, very good. And next, let's introduce the rest, right? The joint and the conditional. Differential entropy. So here, just a straightforward extension of what we have seen before. So now we consider two random variables instead of one random variable, right? For the joint differential entropy, it is nothing but we have a double integral here, fxy log fxy dx dy. Okay, and similarly for the conditional entropy, we have this fxy log f y given x dx dy. Okay, so just a straightforward extension on what we have seen before. Therefore, now we can have the differential entropy of fxy and the gxy. Okay, so we assume this two random variable xy follows x and y and the gx and y. Okay, and then we can see the differential entropy. No, so the relative entropy equals to this. Okay, and although these two may not have a clear meaning, but differential entropy have the clear meaning here, right? Therefore, so we can say the mutual information would have the same meaning as before, right? The mutual information is nothing but the differential entropy, the relative entropy between fxy and fy, the marginal distribution, right? And that equals to this double integral fxy log fxy over fx fy dx dy. Okay, so one immediate remark is that this mutual information has the same meaning as before, as in the discrete case. Okay, so this is a good thing, right? The meaning of mutual information can still be applied here. And because of our definition here, right? So basically, no matter whether they have a clear meaning or not, so in terms of the format, so it is exactly the same as the discrete time case, right? The only thing we do here is we replace the PMF with PDF, right? Therefore, mathematically, all the information inequality before will hold here, except the relative entropy has to be bigger than 0, right? Everything else will hold. Okay, all the identities, so all other information quantities can be defined similarly using the same method, and all identities and all identities for discrete information quantities hold for differential information quantities. Okay, so basically everything we have learned before will hold here. Okay. Any questions? Okay, if no question, maybe let's end here. So next lecture, we're going to talk about the AEP and the other stuff. So yeah, everything will hold pretty smoothly. So there's no surprising thing. Hey, thank you.